So my name is Ken. I work for PagerDuty at their Toronto office, and this is going to be a talk about WatchDog, which is how we use Scala for end-to-end functional testing. So just by a show of hands here, how many people have used PagerDuty or know what PagerDuty is? 1, 2, 3. Okay, half. Looks like okay. So for the half that doesn't know, I'm going to very quickly explain it. So you can imagine PagerDuty is a platform for finding the best person to deal with operational issues. So you can imagine, you have some kind of mission-critical infrastructure. You're going to monitoring around that, and that monitoring system is going to send events. And typically, what a monitoring system does really, really well is send an email. And the problem is, if you get an email at 3 in the morning, your phone is going to beep once, and you're going to sleep through it, and you're going to miss a major outage. And it's going to be really, really bad. You're going to be fired the next day. So instead, what PagerDuty allows you to do is you can have all these events from all these different monitoring systems come into PagerDuty, as well as your CI systems and collaboration systems. And we will ingest all this information and get the right person aware that there's a problem. We're going to get them out of bed. So we're going to do it by phoning them, by emailing them, by SMSing them, by sending a push notification, whatever we can do. And if we can't get the first line of people, we'll get the second line, whether that be the person's boss or their spouse. We're going to keep going until we're able to get somebody awake and alert and acknowledging this incident. And that way we can reduce the kind of mean times of outages. So we take reliability very, very seriously at PagerDuty, right? We have to be up when our customers' infrastructure is not. And because we have a lot of customers, we kind of have to be up all the time. Our customers trust us to reliably deliver their alerts, right? So using emoji, right? We love reliability. Kind of as a testament to this, our architecture actually is a service-oriented architecture, and it's split across multiple data centers. We can actually sustain a black swan event as severe as a data center outage, and that still won't impede alert delivery. So what am I here to talk about today? Well, unfortunately, last year, we had 2 silent Sev1s. So Sev1 for us is all hands on deck, really, really bad. It's 5 customers or more having their notifications being delivered out of SLA. And these were silent Sev1s. These are even worse. This is a Sev1 that happened that we didn't even know about, that our regular monitoring didn't capture. It was kind of in this one area of our code where when an event comes in, we have to decide, do we create an incident or do we not? And it's this really kind of old, hairy, brittle, bad part of the code. And we had a bug. And for a certain small percentage of customers, for a certain integration type, we elected to not create an incident when we should have. And so those people didn't get pages when they should have. So this is really, really bad, right? This exposed gaps in how we do testing and how we do deployment. And the fact that it happened twice, and there were different bugs in that kind of same bad area of the code, not our finest moment. It was actually so bad that our CTO actually implemented code freeze, right? The idea is, look, these bugs happen because code changes. So we're just not going to allow code to change until we can have confidence again that PagerDuty is working properly, until we are confident in our testing and methodologies. So now we were kind of under the gun. We had to get the code to thaw. So we came up with this idea, we're going to write a full end-to-end functional test suite. We want something that will test the functional contract of PagerDuty. If I were to go to you and say, PagerDuty does this, and if you send an event, it will go to be created as an incident. If you send this different type of event, and you wait this much time, then this other type of incident gets created. And for that entire enumeration, we wanted to be able to test that end to end. So we want to do this in a way that behaves like a customer. We wanted to write a system that's going to use PagerDuty in the exact same way that a customer would. But it's a really, really diligent customer that uses kind of the full spectrum of PagerDuty functionality. And uses it really, really often, kind of like Honda. And the idea will be, okay, well, we're going to shout from the rooftops if PagerDuty doesn't work as expected, right? Basically, the idea is we're going to run these tests continuously against PagerDuty, and we're going to alert on failure. Now, some important observations, right? The first is that we're going to be testing the entire system working together. So this isn't, testing a particular service or a particular model. This isn't testing the entirety of the system, but with one service kind of mocked out. This is the entire live system running end to end. And the second is that production is the gold standard for us, right? We want to be running this system against production. And the reason is our customers run against production. They don't run in load tests. They don't run in staging. They don't run in some test environment. They're hitting prod, and so should the system. And that's going to be important because we're going to want to be able to discover issues that might be isolated only to production, right? Some examples are, a configuration change as a result of a bad chef run or because somebody kind of went in and tweaked a value that they weren't supposed to. And also just kind of like general network or host badness, right? Operational issues that can occur. Host goes down, data center goes down, network interrupt between 2 DCs. These things happen and affect customers, and we want WatchDog to be sensitive to that as well. So why am I here? What is this actual talk about? So it's kind of in 2 parts. The first part is going to be a very Scala-focused part. And it's going to be about this library that we wrote in Scala for writing very, very concise tests for WatchDog. And then the second half is going to be just some kind of anecdotes that we've had operationally running WatchDog over the last 9 months. Now, to really understand the first point there, we need to understand PagerDuty's data model. So we're going to take a quick aside. I'm going to explain a little bit more about what PagerDuty does in terms of its actual data model, and then we can see how the tests get written. So with PagerDuty, you have this concept of events, right? And we talked about how events come from different monitoring systems. And events are targeted toward what's called a service. A service has a service key. You can imagine it's a routing key. It basically says, like, go to this particular entity inside of PagerDuty. And a service represents a service inside of your infrastructure, right? Whether it be a database host, your database tier, your web tier, some kind of offline reporting system you have, anything that kind of is of mission critical importance to you. So when an event comes into a service, an incident gets created. Perfect. But now we need to assign that incident. We need to figure out who is the best person to address this particular incident. So associated with every service is this thing called an escalation policy. And on this particular escalation policy, it says, okay, immediately, right at minute 0, look at the ops team schedule to figure out who's on call. So we also have a concept of schedules. If nobody on ops team acknowledges this incident, then we're going to, after 5 minutes, notify the manager. If after 9 minutes, the manager doesn't pick up, we're going to notify the CEO. And these are users. So PagerDuty also has, big surprise, a concept of users. So going back to the schedule here, here's our ops team schedule, right? We can look at it. Today is the 9th. So we can see here that on the 9th, Joe is on call for the week. So Joe is the user on call. And every user has a set of notification rules. And that's the other final entity that we'll talk about. So in Joe's case, right, at minute 0, we want to email Joe. And at minute 0, we also want to SMS him. So he'll receive 2 different contact channels. He'll receive this PagerDuty alert. If Joe doesn't pick up, then after 2 minutes, we're going to phone Joe. We're going to keep going through Joe's notification rules until the incident escalates. Final point is that all of these entities are isolated between accounts. So, we have a notion of account. And this is so, Hulu doesn't see Groupon's users and vice versa. So what is our first attempt at writing a test? This is actually pretty close to the pseudocode that we had when we were first kind of speccing out WatchDog. We're like, what do we want tests to look like, right? So, we have to somehow provision an account, right? You need to use an account to use PagerDuty. Then we'll do this. We have to, kind of create all the data model stuff that I just talked about, right? We have to create a user and a schedule and add the schedule to the escalation policy and add that to a service. We have to create an event that actually gets sent from the test. We want to actually send the event as well. Then somehow we have to wait for an incident, right? We've sent this event to PagerDuty, but PagerDuty is asynchronous. So we need to wait for, a few seconds for it to kind of go through the pipes and that actual incident be created. So somehow we'll wait for an incident. And then we get to the good stuff, right? We can actually validate that the incident that was created is the one that we expected given the event type that was sent out. So there's a couple problems, right, with this, right? So the first is, I have it in the comment here, how should accounts be provisioned? It's kind of a question that we will have to answer. This is gross. The programmer in me hates this, right? There's a lot of boilerplate here, and I would hate to have the same stuff over and over in a bunch of different tests, tweaking only one line because one small value happened to change between 2 tests. And the final one is, again, here was another open question, is how actually should we be waiting for incidents to be created, right? And should we do that synchronously or asynchronously, and what are the trade-offs of that? So we'll discuss some of that as well. So some observations, right? We decided to use ScalaTest as the kind of bedrock for WatchDog. It was kind of between ScalaTest and Specs 2. ScalaTest, I wish I could say we did this elaborate analysis and we compared the pros and cons. ScalaTest had a nice web page, and that kind of just, put it over for us. It's a very robust piece of software. It's very mature. It has a great community. Had a lot of answers on Stack Overflow, so it seemed like a good choice, and I'm happy we picked it. The second point, and this is going to be a contentious one given that I'm at Scala Days with all the reactive folk here, but synchronous polling is going to be okay. And I'm going to come back and talk about why we made the choice to use synchronous polling. And the final one is we're going to be running WatchDog against production. So we don't want to melt our servers in an attempt to verify correctness. So we need to be mindful of load, and a lot of the design decisions that we're going to make need to be considering the amount of load that's going to be generated on the servers. So let's start going through the various issues that we saw in that original test and see if we can make them better. So the first was account provisioning. So this is what we started with, right? We have this trait called an account. An account is just, it has a particular subdomain, like Hulu or Groupon, and a particular auth token that's used to actually access the account. And then, here's our ScalaTest test, right? And somehow we were going to provision an account. But this is kind of gross, right? The responsibility of creating an account is now on the test author, right? The test author is going to have to say new account or something with the account. Well, what if we did this instead, right? What if we pass in an account, right? So as opposed to having the test author have to instantiate an account themselves. Well, let's embrace functional programming, right? Let's actually have the test itself be a function that accepts the account as an argument, right? And then the test is just free to do stuff with the account and no longer has to worry about creating an account or provisioning it. We can move all that stuff away into this other support library. And the way that we're going to kind of bridge that is with this idea of with account, right? And we're going to talk about what this is, right? But it's going to take a test and test is just a function that accepts an account and returns some result. In fact, this pattern has a name. It's called the lone fixture method. Remember I said ScalaTest has a really nice web page? This is actually on their web page, right? They talk about exactly this technique along with a bunch of others. So, specific to our case, right, here's from their docs. A lone fixture method, so in our case it's with account, takes a function whose body forms part or all of a test code. In our case, it's all of the test code, and the function is test, right? It creates a fixture, it creates the account, and here's the account right here. It passes it to the test code by invoking the function, and then it cleans up the fixture after the function returns. And with account is going to do all that. So let's see how that looks. So here's a whole lot of code, but we're going to go through it piece by piece so we can understand what's happening. So here's with account, and it takes in the test itself. It also takes in this implicit account manager, which we'll come back to in a moment. We also have this plural form of with accounts for tests that need to operate on multiple accounts simultaneously. Also taking in the same parameters, this implicit account manager. There's the implicit account manager. And here's the actual account manager trait, and it just is a very, very simple interface. You can acquire accounts from an account manager, or you can release accounts back to the account manager. Both with account and with accounts call this run test and release accounts, which is defined down here, right there. And the body is fairly simple, right? We invoke the account manager, we say acquire the accounts. We take those accounts, that's our actual fixture. We pass that into the test. And then we put the cleanup inside of a finally block to guarantee that it's executed, right? In case the test happened to throw an exception, we don't want to leave accounts just kind of in this half state where they're acquired but haven't been put back in the pool. So now let's consider some load, right? And we have some trade-offs, right? We kind of have two choices here. We can either create brand new accounts each time, right? We have an API, we can just instantiate a new account, maybe delete the account as part of release, or we can reuse accounts from some pool. Well, back to the napkin math. We're going to have hundreds of tests running every 5 minutes. That's going to turn around to be 28,000 accounts created per day. In, I think, 6 months, that would be 5 million accounts. That's a lot. That's a lot of data just to be having, just for the purpose of testing, that's then going to go away. And we were kind of sensitive. You could make an argument, well, why don't you delete the unused accounts when you no longer need them? I don't want to run delete account ever. I don't want to take that risk of, oops, sorry, Hulu, we're going to get you back online any minute now. It was kind of too risky of a thing to do. So we opted to try to go for reusing accounts from a pool. So what does that look like? Well, here's our account manager trait again, right? The same thing. It has acquire accounts and release accounts. And we have this implementation called pooled account manager. And it just takes in a sequence of accounts. And this is just read. We have a static config file. We a priori provisioned, I think it's 100 accounts that just get used and shared between the tests. We have 100 on production and staging and load test. And that just gets passed into this pooled account manager. There's a semaphore and a kind of a free list for maintaining the accounts. As part of the constructor for this class, we immediately call release accounts. This is a Java semaphore, so it starts off at 0. When we call release accounts, the semaphore's value will become all accounts.size. And then in acquire accounts, when you try to acquire it, if you are successfully able to acquire it, then you can actually dequeue accounts from the free list. If no accounts were available, if let's say they're all being in use by all the tests that are running, the test will just block and wait, and that was fine for us. We know how many tests we have, we know what their concurrency factor is, and so we can provision enough accounts ahead of time to make sure that this generally doesn't block. And then in release accounts, we have to do the opposite. First, we put the accounts back in the free list, and then we release the semaphore, right? You don't want to have an inversion here, or else you're going to have a race condition where you think things are released, but they're not actually. One final point also, I wish that concurrent linked queue had this actual API. It doesn't. There's a whole lot more code that we actually have going on here, but this is just to kind of give the spirit of what's happening. And the extra code is basically just because the API for concurrent linked queue is poor, we kind of have to go in queuing one by one and do a fold left, but PowerPoint only gives me so much verbosity, so I've shrunk it down here. Okay, great. So that's account provisioning. Now we can move on to the next part, right? We have this problem of how are we going to set up account entities? So again, we started with the grossness, right? We started with like, oh man, creating a user and a schedule and then an escalation policy and then like we have, kind of a deep data model at PagerDuty, right? And it would be very unfortunate for test authors to have to codify that explicitly in every single test, right? So there's lots of boilerplate here, and it'd be really nice if there was a way to specify only what I need, right? And not have to specify everything. Perfect. Let's use the builder pattern. And we can use the builder pattern to encapsulate setting of defaults. So here's an example, right? Here's, sending an event should create an incident, good ScalaTest, in with account. So this is our account provisioning. And then we'll just create this thing called a service builder, and we'll call create on, and we'll create it on the account using the account that was given. Notice that this is going to create a default service. It's going to pick a reasonable default for the service type, and the unact time, and the auto-resolve time, and all the other parameters that a service has, and the escalation policy. But as a test writer, those defaults are kind of good enough for me for this test. If I do need to override something, the builder pattern allows us to chain. So we can actually say here, right, new service builder dot auto resolve timeout and set that, dot acknowledgement timeout and set that as well. Going one step further, it's not so nice I have to actually explicitly instantiate a service builder in the test. So we'll do this kind of syntactic nicety where we can say builder.service instead. And builder is defined here. We have this singleton builder, which has a builder function defined, and that's actually then going to return a builder picker, and that has service defined in it. We could have also done this instead of as a singleton. We could have mixed in a trait to get builder. Pros and cons of both. We opted for the singleton. It's worked out well so far. What if we have to set up other types of entities, right? So in addition to service, we have escalation policies. Well, that's not a problem. We can just add that into builder picker. And now we have builder.escalation policy, as we see here, builder.escalation policy. And this test first creates an escalation policy builder, creates the escalation policy by calling create on, and then passes that escalation policy to the service. But we can go one level further. Instead of actually creating the escalation policy and passing it to the service, we can just create the escalation policy builder. This is something that's entirely local. There was no call to pagerduty.com made yet. And then pass that into the service builder. And then when we call create on the service builder, it will recursively go through and it'll realize that there's an escalation policy builder, create the escalation policy. If there had been a user builder that was attached to that, it would have also created the user. So create on actually can recursively and lazily create all these entities that are needed. We kind of only need this one final create on at the end when we've done specifying or describing with builders all the entities we want created. So this is great. Tests are short again, right? Before we had all that boilerplate. Now we have this much shorter thing. And again, anything the user omits, we assume reasonable defaults for. That kind of work for most tests. And then tests that need to specify something have the ability to. So this is a point I'm going to keep hammering in, right? The builder itself is a description of the entity. It's not the entity itself. The builder is something that's created entirely on the client. And when you call create on, that actually reifies that entity. Right? Calling create on will actually cause the builder to go to pagerduty.com and create that actual entity like in our production database and then return it back as a resource for the test to use. So let's see how that works. Right? And again, big page of code, but we're going to go through it section by section. So here is the resource builder, and it's just a trait. Takes a type parameter T, so we can have resource builders for services and escalation policies. T we specify as a resource. Resources are just is a different trait. It's anything that really has an ID, kind of giving a nod to RESTful parlance, right, and dealing with resources. And resource builders have a function create on, and it takes in an account. And this is what we've seen. There's also this implicit. This is basically a wrapper for. It's a client for hitting our API, as opposed to like writing all the raw HTTP ourselves. It provides the CRUD interface in Scala for actually hitting the PagerDuty API. So let's look at now a particular implementation of Resource Builder. We'll look at Service Builder. So this is what we've been looking at so far. It also takes a bunch of state. It takes the service type, the EP builder, the acknowledgement timeout, the auto result timeout. And this is a Resource Builder of service. So big surprise, Service Builder builds services. And service is type T here, and it happens to be a resource. Little idiomatic trick to use with the builder pattern, right? Define this type called this. That way you don't have to copy and paste the name of your class everywhere. And then, and these are all the functions that the client will actually call. It calls auto-resolve timeout, and we're using the typical builder trick where we invoke copy on the case class, and that returns a new version of the case class with just the one member different. And here it returns this, which is defined to be service builder. Final point is create on, and we're going to get to how this works, but it needs to be there. So we have kind of the same load discussion to have as we had with account provisioning, right? With these entities, either we can create a new entity each run, like every time we call servicebuilder.createOn, we can create a brand new service, or we can somehow reuse previously created entities. And let's do the math again, right? We're going to have hundreds of tests running every 5 minutes. That's 28,000 services, escalation policies, users created per day. That's a lot, right? That's, again, for us, we don't want to melt our servers, and we also don't want the proportion of, kind of watchdog created entities to actual entities to be wildly out of whack, and this would quickly do that. So we're again going to lean towards somehow reusing previously created entities. So how can we do this? Well, an observation is that PagerDuty's API actually allows querying for entities with a given name. So as an example here, you can issue a get to your account.pager.com API v1 services and pass in this query parameter database. And this will return any service that has the string database in it, right? Steve's database or database tier or anything that has database, right? Straightforward like query. Well, this is lookup, right? Like we can build a cache on top of this. So I want you to imagine, right, that test A had a particular service builder, and it actually reified the entity, right? So now there's a corresponding service on that account for pager.com. And then test B, perhaps it's even the same test, and happened to have been provisioned, the same account creates the same builder. So the description is the same. It would be great if we could get the exact same entity as opposed to creating a new one. The builders are the same. The description of what we want is the same, so we should get back the same entity. So the only question is, okay, so what should the key be, right? What should we pass in as the name of the service? Well, let's use the hash code of the builder, right? The builder is a description of the entity. Then the hash code is going to be a description of the description. So let's look at what that means in code, right? So this is the syntax that we've defined so far, but really, this is syntactic sugar for this, right? Service builder is just a case class, and we can just explicitly define all the fields. Builders are case classes, and the nice thing is that the default hash code implementation will recursively account for all the members in the case class. So as an example, imagine that we had the following service builder here, and these values in green are values that were overridden by the user. These are the non-default values. And this particular case class has this hash code. Great. Now let's imagine that this was using the default escalation policy builder of none, meaning we'll just use the default escalation policy that would be created. But let's say that the test happened to override this, and they specified an actual escalation policy builder. Well, look what happened here. By doing that, the hash code for the service builder changed. The escalation policy builder, in turn, has its own hash code. And the user might have set the number of loops to 6. Let's go one level further. Imagine that the test doesn't want the default escalation policy builder, but they want to have 2 users on call in the first level. Okay, let's watch what happens to the hash codes. They change, right? Here, we change the escalation policy builder by adding 2 user builders. Those have their own hash codes, but that changed the hash code of the escalation policy builder, which in turn changed the hash code of the service builder, right? This is a really powerful concept, that the service builder is a description of the entity, and its hash code nicely encapsulates what that description is in a single number, in a single name. So I feel like I'm flogging a dead horse here, but I'm going to say it again, right? The builder is a description of the entity. So our algorithm then can just be as simple as, we'll compute the hash code for the builder. We're going to check if an entity exists on page.com with that hash name. If it does, we'll just use it. And if not, then we'll create it, and all the dependencies recursively, right? If we are creating a service, we also have to create the escalation policy and the users and everything down the line recursively. So let's see the code for that. So here is resource builder once again. This time, we have no longer create on, but we have get or create on, because it could be doing a get instead. And we now have it being asynchronous also. We used finagle. It's nicer to use finagle in kind of an asynchronous fashion. So instead of returning t, it's going to return future of t. And the algorithm is just as I described, right? We create the moniker, right? We take hashcode.toString. This is the name of the entity that we want to have. We have to find if there's a resource with that name on pager.com, right? And we use the subdomain client to do that, right? This is the piece that's going to make the actual HTTP request. And then if find existing happened to return a no matching resource exception, we create it. Perfect. Async create on and find existing are delegated to the subclasses to implement, right? This is going to be future of t. So for the service builder, this is creating a service. For the escalation policy builder, this is creating escalation policy. And because those are different endpoints, we defer to the subclasses to actually implement it. One small bug that we actually had in our original implementation, the original code was this. It was just hashcode.toString. And we now correctly have hashcode.toString encased in square brackets. So I'll give you guys kind of a half a second here if anyone can spot what the bug was. So remember that like query that we had before? So imagine if the builder's hashcode was 743. Well, that meant that we could get results with anything that had 743 in the name. If we had some other builder that happened to have the hashcode 984743103, that would be returned. And that's not good. Then you're getting an entity that doesn't match the builder description you have. So we fixed it by putting some sentinel parameters here that aren't digits or a negative sign. So final issue we have to fix wearing our library author hat is how we actually have the test wait for things to happen on PagerDuty.com. So again, we started with the ability to send the trigger event and somehow wait for an incident to be created. And I'm going to come back to this now, right? I said earlier, synchronous short polling is okay. So there's two halves to this, synchronous and short polling. So synchronous is okay. Let me say it like this. I love reactive, and I think it's great. And if we had the time, I would have found a way to integrate ScalaTest with a thread pool and make it all asynchronous and have it all work together. But we were under the gun. And a very pragmatic thing for us was just to have the test block while it's waiting for an entity to be created on PagerDuty.com. ScalaTest could be single-threaded that way, and it greatly simplified the model that we were using. The other half is short polling. So PagerDuty has a webhook API, right? So we could have had that WatchDog creates an HTTP listener, and we set a webhook on PagerDuty, and PagerDuty calls back into WatchDog when the entity is created. We could be truly reactive. But again, that seems like a lot of effort and sophistication when we need tests that run and are short, and we need them quickly because we want to have a code thaw. So we went with short polling. And in fact, it's something a lot of our customers do also. They short poll our API, and we're able to sustain it if we do it right. So let's look at what we want to have, right? And this was kind of the API that we came up with for test specifying how to wait for an occurrence. We came up with this declarative syntax where you specify what's called an occurrence, and you have this kind of nice little DSL where you say you want a particular incident on an account, or sorry, any incident on an account, where, and then you pass in a predicate that you want to have matched. And then to get the incident, you call wait for, and you wait for the occurrence. You could also have multiple occurrences that you'd want to wait for. So here's occurrence 1, and you're waiting for an incident on a particular service where the incident number is greater than 5. And a second occurrence where the incident is on the same service, but the incident key is this string here. And we want to be able to wait for both occurrence 1 and occurrence 2. And what we'd love is that wait for should actually transform to a little short polling loop. So when we call wait for an occurrence, it should translate somehow to, this is your regular short poll loop, right? You have your deadline while the occurrence hasn't occurred, sleep. If you surpass your deadline, throw a timeout exception. And as well, it'd be kind of nice to be able to control the timing parameters for wait for, right? We'd like to say wait for the occurrence within this amount of time and check every 3 seconds, right? So being able to specify max time to wait and polling frequency, which are defined here. Some other things also that are good to have, right? We kind of have this general where clause right now where it's up to the programmer to write their own predicate that matches here. A little bit of syntactic sugar, again, kind of using the builder pattern, is that we can instead have this incident on service with incident key as opposed to saying incident.incident key with state incident.trigger as opposed to explicitly having it in your own predicate. So how do we implement this, right? Well, there's going to be 2 entities that we're going to have to deal with. One of them is called an occurrence, and one of them is called an expectation. And the occurrence is the thing that actually returns entities. So in our case, most of the occurrences we have deal with incidents, so occurrences will return incidents, and expectations will wait for occurrences. Expectations are going to be the thing that does the transformation to the short poll. And it's going to be a little hairy to do the conjunction, to do that kind of and that I showed, but I think we're going to be okay. We're going to get through it. So here's the code. So the top level base class is just an occurrence, and it has one function, has occurred. That's it. An occurrence can only have occurred. The first subclass that we're going to look at is occurrence 1 of t, and this is an occurrence that returns one type back. It is an occurrence, so it's going to have a has occurred that has to be implemented by a subclass. It has an apply function that returns just t, and to get the conjunction, it can take another occurrence 1, you can AND with another occurrence 1, and you get back an occurrence 2. And occurrence 2 is now of T and T2. What does occurrence 2 look like? Here it is. It's also an occurrence, so it has to have a has occurred. It takes in 2 occurrence 1s. It has an apply function that returns a tuple of T1 and T2. This is why we need this kind of occurrence 1, occurrence 2, occurrence 3, because the return type of apply happens to be a tuple. Its has occurred is fairly straightforward. It has occurrence A occurred and has occurrence B occurred. And conjunction is, you can take an occurrence 2, pass in another occurrence 1, and then get an occurrence 3. And, analogous for occurrence 3 and occurrence 4. We ended up defining this, I think, for up to occurrence 5, and that was kind of good enough. Nobody needed more than 5 occurrences that they need to wait for. So how do occurrences actually compose? So, I'm going to make 3 occurrence 1s, A, B, and C, and this is just an incident on a service where something is true. Occurrence 2, you can then create with occurrence A and occurrence B, and this is occurrence 2 of incident. Occurrence 3 is then taking an occurrence 2 and ANDing it with an occurrence 1, you get the occurrence 3. Right? Similarly, we could actually collapse all that and just have occurrence A and occurrence B and occurrence C and rely on associativity, and we just get the occurrence 3 out. And then to actually get all 3 incidents, we call the apply function, and we get back all 3 incidents. There's no requirement that the types here be the same, right? We could have had this be a service instead, and we've gotten back a service here. So what does the implementation for this look like? So incidents are the primary thing that we're waiting for. So let's look at incident occurrence. Again, here's that subdomain API object that we've talked about a lot, right? This is the part that makes the call to PagerDuty.com, and it's an occurrence 1. Typical builder pattern trick again, right? We have type this is the name of the class. Here's a bunch of state. Now you'll notice these are vars. This builder was actually written by a Scala neophyte at the time, so this is more a Java-style builder as opposed to a proper Scala builder using a case class, using the copy function that we saw before. We should go back to change it. We haven't. It functions correctly. It's not a big thorn in our side, so we've kind of left it as it is. And then this is the regular builder pattern stuff that's actually called by the client code, right? So you can call incident with states with a particular incident key, and this is invoked by the test. So continuing on, now let's look at has occurred. So this is the meat of the incident occurrence, right? This is the tough part. So it's getting all the incidents, so it's actually invoking the subdomain API client. And it says here, using instance variables. So this is now hitting PagerDuty's API and passing in all that state that we had, right? We're asking for all incidents, let's say, that are triggered on a particular service with a particular service key. All these variables get passed to the subdomain API client and are sent as query parameters to PagerDuty, and PagerDuty can return all the instances that match that. If there's a particular predicate function that was also defined, we can apply it, and that's just applied client side. And then finally, if there were incidents returned, we'll cache what the first incident is, and then we'll just return, the occurrence has occurred if incidents is not empty. The reason we cache just the first incident here, we kind of consider a programmer error if you specify an occurrence that could return multiple incidents, and we just arbitrarily pick the first one. In apply for the occurrence, so when you actually call apply on the occurrence to get back the incident, we could have not cached and made another call to PagerDuty, but by caching it, we kind of avoid an extra round trip to PagerDuty.com to do the exact same query that we already did and we know is going to work. And the final thing is that instead of having to require clients to explicitly create an incident occurrence, we have this function incident. And this is what we saw before in the call site, incident on service. And it takes in as an implicit the subdomain API, which is, it just threads through really, really nicely. So the syntax is in client code is just incident.onService.where, whatever. Okay, so that was occurrences. So now we have to do the other half, which is expectations. So here is the base class for all expectations. An expectation takes 3 parameters, a timeout, the polling frequency, and a delay time. So timeout is how long we want to wait for. Polling frequency is how often. And delay time is, you might not want to have the polling start immediately at t equals 0. You might want to offset it. So we allow clients to kind of specify that. An expectation also has a has occurred function. And then this is our short poll, right? This is poll inside of the expectation function. This is the same short poll function we saw before, using timeout, polling frequency, and delay time to actually continuously short poll PagerDuty until the result has occurred, until the occurrence has occurred. Or sorry, until the expectation has occurred. We'll see how it ties to occurrences. There we go. So now, how do expectations and occurrences actually relate? Well, the first subclass is expectation 1. And it takes in the same 3 parameters as expectation, the base class. in addition to an actual occurrence, right? An expectation 1 of t is an expectation, and has occurred for an expectation 1 is just has its occurrence occurred. As well, there's this function called await result, and this is how we actually cause the short poll to happen in client code. And this is very, very subtle. There's a lot of subtlety here. But what this is saying is call the short poll function, lazily pass in the occurrence, and the poll function is, remember, going to call repeatedly has occurred, which is going to call occurrence that has occurred, and that incident occurrence function is going to hit PagerDuty, and we're going to continually poll. And when it actually has occurred, then we're going to return the result, which is the apply function on occurrence, and then that's the return value of await result. A little bit of syntactic sugar. We have this object here, expect, that also has its own apply function, and this takes in an occurrence 1 of t, and this way clients don't have to worry about typing all of the type parameters in. It does the instantiation, and we rely on the compiler to unify the types appropriately, right? So this way, in the usage here, we can just say expect occurrence, and I didn't ever have to specify occurrence of incident. I can just rely on type inferencing to do work for me. Final thing is we specified that one thing we wanted to do is be able to control the values that we had for timing parameters, right? We want to expect an occurrence within 15 seconds or checking every 3 seconds. So how do we do that? Well, here's the base class of expectation again. The builder pattern, once more. Here's within, check every, and wait at least. One kind of oddity is that because expectation is an abstract class, we can't use the copy function that we use with case classes unless we defer to the subclass to do it. So there's this function called copy protected, and this is, it needs to be implemented by all the subclasses, and copy protected, for the subclasses, which are case classes, can just invoke the regular copy function. They pass in the occurrence, and then the other 3 parameters come in automatically. Okay, great. So we're done. We dealt with all the issues. So how did we do, right? Let's kind of compare before and after. So once again, this was our first attempt at writing a test. And this was the big, long, gross, and this grossness here. And we didn't know how we were going to wait for incidents. This is the final version, right? Using all of these, the support library functionality that we've just talked about doing. So we can see here is with account, right? And passing an account instead of relying on the test to provision. And it's using the account acquiring trait we talked about. Here is using the builders again to actually provision these various entities from PagerDuty.com. And here is incidents and, here are occurrences and expectations working again to make for a very nice and concise test. One final bit of syntactic sugar I'm going to talk about. This bit here, so this global config is a singleton that just has a bunch of credentials for all the accounts that we provisioned. So this is actually where the kind of account list lives. And we have, again, I think it's about 100 accounts for production and load test and staging. And then PagerDuty spec is just defines a lot of the implicits that we have, right? So we have an implicit for the account manager that's actually used by with account. I don't know if you guys remember there was an implicit that was there. There's a subdomain API client that's actually used by incident here, and there's an implicit for that. And as well, there's a separate HTTP client that we use for event.send because sending events to PagerDuty goes to a different endpoint, so we have a different HTTP client. So we have a separate implicit for that. So PagerDuty spec kind of takes care of defining all those implicits, so tests don't have to worry about explicitly defining them. So that takes care of the programming part. So now I'm going to talk a little bit about our experience running WatchDog in production. So we currently, I did a grep just before this talk. We have 114 tests, and we run them continuously in production. And we separate them. We partition our tests into different rings. So we have the shorter tests, things like create an event, and you expect an incident to be created. Those tests don't take a long time to run. We can run those every 5 minutes. Other tests take longer just by virtue of what we're testing. As an example, you can imagine send an event and then wait for it to escalate. So you want to wait 5 minutes, and then you want to wait 6 minutes for it to escalate again. So that test is going to take at least 11 minutes to run. So tests that take longer, we run on a different cycle in what we call a different ring, and those we run every 30 minutes. So now this is kind of the fun part for me, right? Some issues that we actually found. When we first wrote WatchDog, we found that we actually had very slow in queuing events. When customers send events to PagerDuty, there were some timeouts. We actually set the WatchDog timeout for event and queuing to be 20 seconds. And it would take longer than 20 seconds in the P99.9, right? And this is something that our regular monitoring didn't ever capture because we never really, set it that high. We generally look at like the 99th percentile. But we were able to realize that there was a couple different ways that we were using Cassandra that weren't quite correct, and we tweaked a lot of timeout values to really ratchet that down. And now this no longer fires, right? This was kind of a surprise for us. Load balancers throwing 502s, so we use load balancers, big surprise. We have our highly available queuing service. This is the service that events actually go to and they get queued by. And what we were doing is that we, in the interest of security, had a TLS connection between our load balancers and the service is called Caster, this highly available queue service, except that we did it wrong, and we had a new SSL connection created on every single incoming event. So that very quickly saturated the CPU of all the Caster hosts, and as a result, there were no hosts available, so the load balancers returned 502. We ended up actually just doing away with TLS. We ended up using an IPsec VPN between all of our hosts anyways in our infrastructure, so that we found that problem and solved it. 500 is due to a database node changeover, so we use Percona. We run it with a single master and a bunch of slaves, and we were cycling which the master is and vertically scaling it, and we were getting a couple 500s. We have regular alerting around that, around what our 500 count is, but we only actually alert if I think it's more than 0.1% of requests result in a 500. Well, WatchDog doesn't care about that number. WatchDog just cares, was there a 500 or not? Did it experience a 500 in the same way a customer would? And we did, and then we were able to kind of like babysit this database migration a whole lot more. We actually caught a functional change with WatchDog. This was a breaking API change that was kind of accidentally introduced. We are staunch believers that the API contract is sacred, and you should not break it. And this particular one was this behavior where we wanted to create a notification rule automatically when a contact method is created. And that was done in the API, and WatchDog caught it because it kind of violated some of the assumptions WatchDog was making. We instead, changed this to operate in the app. Load balancer change, this was a fun one. There was a load balancer change that went out, and it was kind of the wrong thing. We have a bunch of workers that are responsible for executing timers. So you can imagine an incident has to escalate after 5 minutes. So there's a worker that's responsible for, at 5 minutes, run incident.escalate. Except that because of this load balancer change, all the work, instead of being done by our fleet of workers, was being done by exactly one host. And we didn't notice this immediately because we didn't have a lot of load coming in at the time. And then we got a little bit of a load spike, and then that one worker became saturated, and then WatchDog started timing out. And then we realized we had this load balancer issue, and we were able to fix it. The final one, and this is actually very recent, Linode Fremont had a huge outage on May 30th. WatchDog caught it. Our regular monitoring didn't, right? We, again, rely on our architecture being cross-data center. So we can sustain a data center outage, which happened here. But WatchDog is sensitive to, in this case, an event coming in, and then because the host was down, the event wasn't processed, and WatchDog got a 500. Fortunately, our GSLB kicked in 30 seconds later, took that host out of the rotation in DNS, and as a result, future events started working. But WatchDog was sensitive to it and found it. And of course, countless of other issues as well. We now kind of require for big changes that WatchDog be run in staging and load test. So kind of some other learnings, right? Rare anomalies, exercise repeatedly will fail. But you kind of get in this tight loop where if you are religious about running your tests every 5 minutes or 10 minutes or 15 minutes, and then being diligent about fixing issues when alerts happen, you'll quickly surface non-deterministic behavior, and you'll quickly converge on a more resilient system. There's a lot of expectations on client behavior. One issue we had with WatchDog was with how it deals with mail. We were using the JavaX mail libraries, and they don't operate exactly as most MTAs do. At PagerDuty, we have a bunch of different mail servers that we use, but JavaX only knows how to use one, and that one is down. It doesn't know how to fail over, so we had to kind of change that client behavior. There's this trade-off as well between timing and false failures, right? If you want to have really, really tight timing bounds, you're probably going to be getting alerts a whole lot more, and you're not really going to be, you could even consider them false positives because they're not actually indicative of any failure. It's just PagerDuty is an asynchronous system, and sometimes it does take a few seconds for an incident to be created. The flip side is if you make your timing tolerances too long, you're at risk of having increased latency for detecting errors. WatchDog tests the system, so I guess it goes without saying if the system is unstable, the test will be unstable. And this actually ties in very much to the next point. A lot of the failures that we see are transient system issues. Right? There was the one functional change we saw, that breaking API change, but by and large it has been a network blip or a host going down. And the nice thing with WatchDog is that because we are diligent about fixing them and tweaking timing parameters, we're able to shake out a lot of these things. So I'm happy to say that PagerDuty I think is much more resilient now than it was 9 months ago. Final thing is that lots of tests incurs lots of load. So I think WatchDog right now is between 5 and 10% of our production traffic. I think if we had done the work of actually not reusing entities and reusing accounts, it would have been much higher. It would have been 20 to 25%. Our hope, though, is that kind of as our customer base grows and our fleet grows, that this percentage will become smaller and smaller. And that's it. Are there any questions? I have T-shirts for people who ask questions. There you go. Wow, that always works. Yeah, so again, we have 114 tests. I think it takes about 30 minutes end to end. So you just basically kick off WatchDog on load test to do one run, and then go to lunch, grab a coffee, come back 30 minutes later, and if it's all green, go ahead.
But after one run, we are happy with this. If process, garbage collection or some more problems.
Yeah. Yeah, so I guess your observation is maybe there are more finicky issues, right? We're kind of using WatchDog to make sure, when we run WatchDog and load test, we want to make sure that we're catching functional errors, right? Issues like, GC timing, or maybe there's some weird race condition between hosts. Those are a lot more subtle, and we're not going to expect developers to find those necessarily in load test. We're fine to find them in production, and that's why WatchDog will be run there. Right. We do. Yeah. Again, this goes back to the fact that we pre-allocated the accounts for WatchDog. So we have a prefix that we use for these WatchDog accounts, and so basically any account that matches that prefix, we don't include in any of our reporting metrics. Yep. And I'll come up after and I'll give you a T-shirt. Yeah. We do, right? Like, again, we partitioned our tests into rings. So we have the shorter tests and the longer tests running on different hosts in parallel. But we do kind of on a single host run the tests serially because of the observation that we made earlier about running tests with synchronous polling in a single threaded fashion. We could maybe run them in parallel. We didn't create the pooled account manager to be aware of multiple hosts. So we're not like using Zookeeper to lock, right? We're just using a local semaphore in that one process. And what we do is for the long running tests and the short running tests, we just give different sets of accounts that they should run on. So no, I guess is the answer. But I'll give you a T-shirt. Yeah?
What do you do to fill out this transient issue? Because there's nothing worse than having a system that fails once in a while.
Oh, no, yeah. So we're very diligent, right? Like, we have an on-call rotation, and WatchDog is part of our on-call rotation. So if you receive a WatchDog page and you're the on-call person, you are expected to start investigating what's happening and either file a ticket if you can identify where it is with the appropriate team, or if it is your team, going ahead and fix it. Like, and that's the thing. That's the reason why we become more resilient. If we just kind of let these things sit there and it's like, oh yeah, this happened again. Why? PagerDuty would not be improving. In the back, yeah. It's pretty isolated, right? Like, we still rely on people to write unit tests and write integration tests. And remember that brittle part of the code I talked about earlier? We've gone through a project now to actually refactor that so it's not as brittle and has better testing that's isolated to that particular unit. But WatchDog is kind of like this catch-all that, in addition to all these various other testing methodologies, we also have this kind of end-to-end functional test that we can also run. I wish I could say it's like it has improved our testing culture. We thought we had a good testing culture, but we're missing this big glaring area, and now we filled it in with WatchDog. I think time for one more. Yeah.
So I understand you had a kind of a code freeze when
Yep.
you started this. How long did it take you to actually get it up and running and release the code?
It was about 6 weeks from kind of start to finish, right? It was mad because it was. Myself and someone else were writing the support library, right? Kind of all the things that you see here. But we also had all the other developers waiting to want to write code, so they were all put on WatchDog also. And so they were ready to write tests, right? We kind of had an army of developers ready to write these 114 tests. So it was kind of back and forth where we would work with them to, what do you need to make the tests more concise? Oh yeah, you have to wait for things. Okay, well, write something. Then they would take that and write some tests, and it was very iterative, right? So we came to this so I'm kind of cheating in this talk in the sense I can present the final solution. There was some kind of back and forth with the test authors to kind of converge on a good API for tests. Okay, one more, and then we should really go.
So you mentioned that if you have a severe one, then you have to go out and fix PagerDuty. But how do you get notified when PagerDuty gets down?
An excellent question. So we have the different severity levels. For the lower severity levels, we use PagerDuty. For the higher ones, we have, I think, 2 or maybe 3 now different monitoring systems that we use that are checking our status page and other kind of important metrics for us that will page us either through SMS or through email. So we have, they're essentially using very lightweight competitors of PagerDuty to notify us. But we're friends with them, so it's okay. All right, let's leave it there. If you have any more questions, I'm around afterwards. Please come and ask. And anyone who asks a question who wants a shirt, I have a few extras also. Please come up and happy to give them out. Cheers, guys. Thanks.